Awesome. Welcome, everyone. We'll get started here in a couple minutes. Let some people join in from the Discord. I'll share this link with you too, Brian. Really excited to have Brian Chen, the co-founder and CTO of Acala, joining us today, his morning, early morning. So yeah, really appreciate you taking the time. If you guys have questions throughout this, drop them into the YouTube chat. And then at the end, we'll do some Q&A and be able to answer any of those questions for you. And we'll just give it about 30 seconds. Let some other people join in here. Also, make sure to stop by the Acala Discord channel. And if you have questions in there, just drop them in. Otherwise, yeah, Brian, if you're ready, we can go ahead and get started.
Yep, thanks for having me. In today's workshop, I'm going to talk about how to deploy smart contract in the Akala EVM, and I'm going to just do a quick demo of implementing a simple arbitrage bot using Oracle and Scheduler. So everything will be running on-chain, so there will be no off-chain components in this bot, so which is the interesting part that you cannot really do it on the Ethereum currently. So so the agenda will be out talking about to give us some quick overview of Akala and describe some unique feature of the Akala EVM and how to deploy Solidity project into the Akala EVMs because we are not 100% compatible with existing tools, so there will be something you need to be aware of. And in the workshop part, I'm going to show you how to implement and deploy a fully automated on-chain arbitrage to the Akala EVM. So start with Akala. So Akala is a DeFi hub for the Polkadot ecosystem. So we provide a few DeFi primitives, so that's including a multi-character stablecoin, and also provide a liquid dot staking derivative. So you can stake the dot and exchange for L dots, and then which can be used to issue a stablecoin. We also offer a simple AMN exchange, decentralized exchange on the chain. And we also have a decentralized sovereign wealth fund. So the funds controlled by the governance. So we have a live testnet now. So current testnet is a TC5, but we're going to just release a new testnet with the fully updated Akala EVM feature TC6 in the next week. So Akala aims to be a DeFi hub. So we also we self have built a few DeFi primitives after that show, but also offer smart contract platforms with EVM capability. So people and other projects will be able to leverage all the existing DeFi protocols of Akala and deploy your own DeFi applications on top of it. So this is a high-level architecture of Akala. So Akala is a parachain of the Polkadot. So all the applications built on top of Akala will be enjoying the shared security of Polkadot. So it will be using the DPoS. So there's no need to worry about the mining and all the unstable block time, etc. And we'll be able to enjoy all the parachain ecosystem of Polkadot. So there will be different kind of parachains and bridge to Ethereum, bridge to Bitcoin, and other parachains connecting to Polkadot. And with the shared security, we can easily do cross-chain communications between parachains. And so all the applications built on Akala will be able to access resource and assets in other parachains as well as in other bridge chains, including Ethereum and Bitcoin. So Akala, we have built a few protocols within the network, and on top of the protocols, then people will be able to write smart contracts and build your own DeFi applications deployed in the Akala EVM. So so that's all the overview of Akala. So let's get into the technical part. So for the development of the smart contracts, one easy way is just run your local node. So we have the Docker command. That's the easiest way. Just run a simple node. There's also nodes have a special flag instancing, so this means it will produce a new block as soon as the transaction appear in the transaction pool. So there's no need to wait for a few seconds of block productions per transaction. So it just makes things a bit easier during development. We have also EVM examples. So this have all the this also having this Docker command will be inside this README file, and for all the examples code I'm going to show you today. Just one thing to keep in mind is the goal of Akala EVM is inherit the goodness from Ethereum, which is the developer community, all existing projects, and the mature ecosystem and development tools. But we all know there are some legacy decisions on Ethereum that things can be improved, but cannot be improved due to various reasons, or still pending for new EIP to be merged in a hard fork to resolve the issue. As Akala is a new project, we want to inherit the good things, but not all the legacy decisions. So we want to improve the existing EVM ecosystem. So because this means if we want to become 100% capabilities, we need to inherit all the legacy decisions. So this will be a tough decision for us. So we have made a decision to improve for the existing EVM, which means we're not going to gain 100% capability, but of course, we're going to make a lot of improvements. So hopefully, we also provide support and make sure all the changes are easy to migrate and minimum change required. So most of the existing projects can be just deployed without change, with minimum change on Akala EVM. Some of them might need some change here and there, but it should be all fairly minimum scoped. So those are a few unique features of Akala EVM that I'd like to highlight. There's a lot more just working in progress, so will be coming in a later version of the release. So we also we have a lot of system smart contracts. Those are the bridging between the Akala EVM and the Akala runtime, which is the one we're having all the Polkadot features, such as bridge, all the Akala protocols, such as stablecoin protocols, and other bridge assets, which including, for example, the bridge dot and bridge to Bitcoin. So those are the address of all the system smart contracts. You can easily recognize their system smart contracts just by looking at the address. Obviously, we can pick whatever address we like. So we just picked one with just pick those numbers. So let's start with the mirror token. So actually, you can see that we have for every tokens in our network, we have created a mirror token. So this is a ERC20. It's very similar to a wrap token like WETH, but there's no wrapping required. In order to use WETH on Ethereum, you need to wrap it first, convert ETH to ERC20, and then you need to redeem it or wrap it later if you want to get the original ETH back. So this obviously is more transactions and more work. And it's also confusing for the users as well. Because we have the full customizability on the EVM itself, so we can just expose the underlying storage as the EVM, so as a ERC20. So this is just a new interface, but it's sharing the same underlying storage of all the native token. So there's no wrapping required. If someone sends you some dots from the Polkadot religion to the Akala parachains, and then you can query the value on the smart contracts, and you will just read the value. And if you spend do a ERC20 transfer of the dot tokens to another smart contract or someone else, and you from the substrate side, so the Akala runtime side, you will see the change appeared as a normal substrate smart contract transition. Just to quickly show you this. So this is the Akala EVM. So currently it's connecting to our new testnet TC6. So we have preload. This will be the primary tools, like the UI tools, can be used to integrate with the Akala EVM. So we have preloaded a bunch of like system smart contracts. And then here we'll be able to select, for example, this AC is our native token. So it's all ERC20. So you can just using all the standard the ERC20 features. So I can query my balance of this account, and I can make a transfer. So I need to, well, I can just transfer myself. So this will be equivalent to a native transfer. And so you can see the transfer success, and I query my balance. I'll transfer myself. The balance doesn't change, but it does. There's a transaction fee involved. So you see the sum amount of fees deducted from the transaction fee. So this means like this during the development, then the smart contracts will be just easily access the native tokens without worrying about like wrapping the tokens. Another unique feature we have is the scheduler. So this will allow smart contracts to schedule a call after a number of blocks to be called. So we will reserve some transaction fee upfront and refund the unused fee after a call is dispatched. There's no guarantee the schedule call will be called on a particular block, because obviously if things are blocks are full, things are busy on the network, then the schedule call are lower each priority, so they could be delayed. But at least it's possible to schedule a call with their offline components. So there's no need to, for example, build a bot to trigger a particular rebalance smart contracts on your every day or every one for once in a while. So this will make us a lot of things much simpler and easier. So again, this will be a system smart contract. So so you can see there's just a schedule call. So we have a bunch of parameters. So contract address is the contract you want to call. The value is the native token you would like to send along with the call. You need to pass a gas limit, storage limit. So we have a simple state renting system. So the storage limit will limit how much additional storage can be used during this call. There's also minimum delay. So you can schedule this to be after, say, 100 blocks. So it will wait at least 100 blocks to call the smart contract. And the input data will be just the data to be invoked along with the call. So it will be the selectors and all the arguments. So this is basically how to schedule a call. It should be very straightforward. Join the testnet to keep things easier. So I've disabled the fees. Well, you still limits applies, but there's no fees reserved when making a schedule call, just to keep things easier. Will be enabled again in the later testnet. So this basically means people will be able. So this is just one-time schedule call, but you can, of course, in a method to be called or in the smart contract to be called itself, can just schedule another call. So this is the way to implement recurring payments if needed. So this is the interface. We also have some other methods that can be used to cancel the call and manage the call. So just to quickly show you the code. Oops. So we have a lot of examples. Like for example, there's examples for the scheduler. So we just check things here. So there's a smart contract interface. So in this pre-deployed contracts, you can see all the system contracts. So you can check the schedule. So this is the interface. So you can schedule a call. There's some events. You can cancel a call to be. You can also reschedule a call. So to use it is very simple. Just passing all the parameters, the right values, and just API code signature of the things you want to call. You can also pass additional parameters. So it's just pretty standard encode. So this will allow, so in the pay function, it will first require this can only be called by itself. So someone else cannot just maliciously trigger this call. But of course, it still needs to be public to be called. And then if needed, so this can schedule another call to be called in the future. So this will reduce the count by 1. So you can upfront say that I want to call this 5 times for every 3 blocks, and every time this will reduce the count by 1. So this can be used to implement a simple recruiting payments. Of course, you can, all the code is available, so you can study it in detail later. So another feature we have is Oracle Gateway. So that's as the Acala, we have a few device primitives. One is the stablecoin, which of course needs Oracle to access the price information of the cryptos. So we would need the Oracle. So we have created Oracle gateways, and various protocols, including Chainlink, will be feeding the price data into the Oracle. So other we also expose this as a solidarity interface. So other dApps or the smart contracts built within Acala EVM will be able to access all these price data using this interface. It's very straightforward. Just get the price of a particular token. In a later revision, we'll be also adding more APIs to get more fine-grained detail. So, for example, you can just read information from Chainlink for this token. So just another quick example. So we have this, so let me actually copy the dot address, and we have the Oracle. So I can just get price of dot, which is almost $36 now. So currently it's all 18 decimals precision. So that this is also including a timestamp, so you know when was the last feed of this token, so you can determine if this is too old or something. Yep. So now, yeah, I've shown you all well, not all, but most of the interesting feature. So we can start just deploying things on our testnet. So this is the Acala EVM. So the first you need to, so by default it's connecting to the TC6 testnet. You can also switch to the local node, or it's switching. Yeah. So you can also use custom endpoint. So if you deploy your nodes on a server elsewhere, you can just change the endpoint. So that's connecting to TC6 for now. In order to use this, you'll need to have the Polkadot extension installed. So, and then you need to create a new account in the Polkadot extension. And after that, you can use the faucet to request some file. So right now, this faucet button is not really integrated. So later I'll make this actually give you some testnet token on the TC6. But once you have some test token, you can either create the EVM address that's using MetaMask and bind this with your account, so you can use the MetaMask to sign messages. Or the simple way is just we'll use auto-generated EVM address from the account address. So it doesn't have any private key, but you can use the Polkadot.js extension to do the signing. So that's with the binding account, and then you'll be able to just deploy or call smart contracts. So you can use Remix to deploy or compile the smart contracts. Because we are not using MetaMask, so you won't be able to using Remix to, well, at least for now, you can use Remix to deploy the smart contracts, but you can still use it for the development and to compile. So this is a simple ERC20. So you can just compile this code, After it compile, you see this JSON file, and you just basically save this to your local DEX, and then upload here. So I can, and then just upload the JSON file, and then you have this thing uploaded, and then you can deploy your smart contracts. After deploy, you have this smart contracts here, so you can just execute it. So again, I can just query my balance, and you can just using all the methods, or you can make transfer. Yeah. So it should be. So this is the easiest way to using that purely the GUI, the web front end to build and deploy the smart contract into the Acala EVM. But for a more large-ish project, you probably want to have some build script and instead of using Remix. So we have created a JS SDK. It's called Body.js. So this one is one will be needed to deploy smart contracts into the Acala testnet. Because we are not 100% compatible with the Ethereum RPC, we'll be using the substrate RPC to do the deployment. So this will wrap the substrate RPC and expose the Web3 providers. And then you can use your existing Ethereum to JS SDK to access the Acala testnet. So, so this is like for Uniswap's example. So there's some pre-built Uniswap artifacts. And this is the setup code. So it's basically creating a provider from the body, which will connecting to the WebSocket provider from the Polkadot JS. So passing the, in this case, the WebSocket endpoint, the connecting to the local testnet. Or you can make it connecting to some remote server. Let's create the wallet, or it will use the testnet key alias, so we should have a lot of test token in the local testnet by default. And then set up the wallet assigner. So this one will be just a standard the Ethers JS wallet. And then from now on, you can just using the standard Ethers to interact with the blockchain. So you can just create the Ethers contracts. So that's all for Ethers. Deploy smart contracts, and those just the normal workflow on the Ethereum. So in here, you can see deploy the Uniswap smart contracts and approve some token, add some liquidity, do a bunch of things, and disconnect. So that's how you deploy the Uniswap smart contracts to the Acala testnet. I won't run this because I'm going to show you this arbitrage bot. So for the normal arbitrager is that because we have the DEX in Acala testnet or in Acala network. So obviously, then for every DEX there will be arbitrage opportunities. So you say on our DEX, say we have that trading pair of, for example, DOT or REN BTC, or other cross-chain Bitcoin, for example, like Polka BTC. And if you see the price between, like say, the DOT price in our DEX is different than the other centralized exchange, then you'll be able to make some arbitrage. So they will be either buy in our DEX and sell on the centralized exchange, or do the other way, just buy on the exchange and sell here. So in this example, I'm going to show you all the on-chain components. So but you can mostly existing DEX arbitrager, they will be just either arbitrage between multiple DEX, or they will be arbitrage between DEX and centralized exchange. But they usually are needs to be triggered by have an offline server sending transactions to the blockchain to trigger arbitrage opportunities. But with the scheduler, we don't need to do this. That we can just having the smart contracts, the schedule call, so it will just run, for example, every 5 minutes to check if there's arbitrage opportunities. If it is, then it can just do the arbitrage trade. So so this is a very, very simple arbitrage. Is using a strategy that will probably make you lose money. But of course, you can build on top of this to develop some better strategy that will be actually profitable. You can see, so we're taking, so in this particular example, I will be using the Uniswap as the DEX to be arbitrage. Later, you'll be able to use the similar API to access the Akala DEX. Yeah, so for now, so in this code, during the deployment, we'll actually deploy a Uniswap smart contracts that's similar to the other Uniswap example. We'll be adding a bunch of liquidities, adding a DOT and AUSD, the stablecoin trading pair. So people will be able to trade DOT and AUSD in this. And then we'll be deploy arbitrager and say we would like to arbitrage this trading pair and deposit some money. And then we'll just run it. And then without any other offline transactions, arbitrage itself will just run and making trade based on the Oracle price feed into feed by the Chainlink or some other Oracle providers. So in the code, you can see, so it's just, it will schedule itself a call. It will call itself. And there's no value to transfer. There's a gas limit, storage limit, so just some large, big-ish number. And because there's no fee involved, so right now this will just always success. But at later version, when fee is enabled, then you need to make sure this number is not crazy large. And you need to make sure the smart contract itself, when you deploy the smart contract, you have sent some native tokens for it to be used as the trading fee. So during the constructor, you can set the period and how frequent you want to run this arbitrage bot. And then every this period, it will just call this trigger function, which is this one. So the trigger function itself will require it can only be called by itself. So this basically can only be called with scheduler, like other people cannot trigger this externally. And then it will immediately just schedule another call to be called at later. So this will make sure it never stops. Well, it will only stop when this run out of tokens as a transaction fee. So then you will be able to well, just deploy this and forget about it. And maybe come back later, see it's making a winning strategy, so it's accumulating a lot of money, or it's losing money, so it's then it will run out of fees and just stop running anymore. So we'll be using the Oracle. So we have deployed address contracts. They will having all the address of the system contracts, which including the scheduler and Oracle. So we can use the Oracle interface and using the get price to get the price feed by the Oracle. So in this case, we just ignore the timestamp, which probably not a good idea for production ready contracts, but for the demo purpose, we'll just ignore it. We'll check how many token we have for the trading pair. We ask the Uniswap what's the reserve tokens. So basically, get the price from the Uniswap, and do some math to figure out if the price of the Oracle is higher or lower than the price in the Uniswap. This is super hacky, a simple way. There will be some helper libraries from the Uniswap to help you to do this properly. And after that, when we figure out if we want to buy or sell, then we just figure out how much to buy and sell. So in this case, we're just using the 10% of the free balance we have. of course, this is a very poor strategy. You probably want to figure out that by looking at the price difference and the liquidity to figure out the maximum amount of tokens you would like to trade. But again, you can just try to figure out yourself. There are some Uniswap examples on calculating this part. But to keep things simple, we're just doing this. If the amount is not zero, then we will just do this trade, sell this amount. The path will be depending if you want to buy the first token or sell the first token, and just all the risk fund send it to this contract itself. So this is the arbitrage code. It's very straightforward, a simple strategy. If it is making a profit, then itself can just run, well, hopefully forever. But if it's losing money, or if it's lost all the money, then it will have no fees to pay, and it will just stops. Then for production ready, you probably want to have some external controls. Like for example, you would like to pause this contract to make sure, to cancel the schedule, etc. But those are up to you. You can also maybe ask the one of the Hackathon idea, just build on top of this to make this production ready. So the setup code is same as Uniswap, just setting up the RPC endpoints, the keys, and then using the body, you get the Web3 provider and the wallet. And in the deploy, this will just deploy a standard Uniswap, and then deploy the arbitrager and send some money to help it get started. And just we're also using this API to feed the Oracle price, because I'm going to run this in a local testnet. So the LS key will have the permission to feed the price. So you can just write some script to manipulate the price and see how this arbitrage will run in action. Because we're running, the local test is running with instantiating mode, so what it does is basically produce a new block on transaction. So for scheduler to work, it needs to wait for a particular block. So we have this code that will send a dummy transaction just to trigger a new block. So I can just run this. Oops. So let's deploy the Uniswap block. So this is the Docker image I'm running, the local node. So you can see, well, I've enabled a lot of tracing logs, so you can see all the inner details of the smart contracts course. So you can see after running, you have successfully deployed the arbitrage, deployed the Uniswap contracts, deployed the arbitrage book. Initially, you have this amount of money, and then it will feed some value. So in this case, we'll make the DOT token more expensive than AUSD. Initially, during initialization, trading period adds the same amount of DOT and AUSD, so the price will be 1-to-1. But if I make the DOT more expensive than AUSD, then the arbitrage bot will figure the DOT on the DOT price in the DEX is lower than the market price. So it will just do some trades to arbitrage the trade. Oops. So actually, I think there's some, yeah. The initial run have some issues because I just started a node. It doesn't have any Oracle feeds, so I need to rerun it. So it has some existing feed. I probably need to have this line before all deployment. But anyway, so in this case, you can see initially I have this amount of token, and it will just figure out the DOT price is higher, so it will spend some of it US dollars to buy the dots. So end up being having this amount of tokens. And after I've set this run the bot every 2 blocks. So after 2 blocks, it will arbitrage, it will schedule will be scheduled again. You will see another 10% of the stablecoin will be used to purchase dot. And then I have make it so now the stablecoin is more expensive than dot on the dot price and decrease much more. So now it will try to sell amount of dot to buy to get back some stablecoin, and just keep doing this until the price of the DEX match to the price of the Oracle. So you can also in the Polkadot JSX, I can just connecting to the local node to see the actual transactions in action. I need to just rerun it. So you can see, well, it basically produces a new block for everything. So let's start from beginning. So there's a bunch of EVM creators. So let's deploy smart contracts. There's so create a smart contract, and then you can see, well, probably just pick some example. Maybe this block. So in this block, you will see there's no actual transitions. There's only a system remark, the dummy transition to trigger the block production. But actually with multiple, and then in the scheduler, you can see all the events associated with this call. You can see all the event log, which will be the logs from event itself. You can also see the currency logs, the substrate runtime log. So you can see in this case, this amount of dot is transferred from this account to this account. So those accounts will be the corresponding account of the arbitrage bot and the Uniswap trading pair. So you can see, so in this case, this amount of dot is traded with this amount of stablecoin. And you can see that this event transaction is executed. So the schedule is dispatched, but it's also schedule something else to be called on the block 47. So in this case, you can see all in the details of how the thing run in action. So this is my all the work needs to write and deploy a simple arbitrage bot that doesn't need any offline components, that you don't need a server to trigger the bots. You don't need a server to monitor the price. You don't need a server to just figure out how to do different things. Like at later stage, that we could have multiple DEX deployed on the Akala, like with the Akala swap, and then for example, someone else might be deploying their own version of the Uniswap or some other DEX with different trading algorithms, bounding curve, etc. And then you can easily just write this arbitrage bot, maybe trigger every hour. They will seek for the arbitrage opportunities and perform the arbitrage trade. All is just deployed and forget about it. And if it's making profits, then it will just run self-sustained forever. If it's not making profit, and then you can of course have some damage control and then have itself kill itself, or it just run out transaction fee and get killed and not be able to reschedule again and just die. So this will be allow a lot of new interesting creation of a smart contract. Is actually just a self-involving, could be a self-involving contracts that it doesn't need an owner. It can itself can make money for itself. So this all the demo I have for you today. So for the Akala's challenge, we have 2 challenges. So first one is deploy a dApp on Akala. using the Akala EVM. So it should be fairly straightforward. Just follow the thing I've just showed you before. You can either build those projects using the remix and download the JSON file and deploy it using the EVM playground, or you can just using the waffle to build your project, and you can use the Body.js to deploy it to our public testnet, or to deploy your own local testnet. You just need to make sure you can show us that you have actually deployed this to Akala testnet, for not just, for example, the Koban testnet, because the goal is be able to deploy your contracts in the Akala EVM. The Chinese tool, which is a better price, is build a DEX that not only deploys on Akala EVM, but it's also using the on-chain scheduler function. There will be a major plus if the smart contract integrates with Oracle's, say, and if this allow you, say, in future access the Chainlink data price. Like for example, the Arbitrage bot is the perfect example for the Chinese tool, but of course you cannot resubmit it. But you can maybe, like as I said, there's a few things, a lot of areas can be improved. So maybe you can build on top of it, or you can build something else. For example, some subscriptions, payments, or I don't know, and a lot of things that can use on-chain scheduler just to make a lot of things much simpler. So you just update and build a smart contracts using this feature, and of course you still need to demonstrate how to deploy it to that kind of EVM. Another additional bonus will be if you can have the front end connecting to the smart contracts. Again, you will be also using the Body.js to do the connection between the Ethers.js and the Substrate RPC. But as I showed you before, it's very straightforward. Just in the depth side or in the front end side, you mostly just need to worry about Ethers.js, which is a standard Ethereum library. So the next step for you will be check out the Akala Hacker Guide with all the resources and links. Also join the Discord, Chainlink Discord server. We have the Akala channel here. So feel free to ask any questions, and I and some of my mates will be able to help you there. And wow, and just get start hacking. Hopefully you'll be able to build something amazing. Yeah, so this is all the useful links you'll be able to find. So this including the hacker guide and the EVM playground, all the system contracts if you want to check the API, etc. And of course, all the examples is in the EVM examples, and the blockchain nodes is here. Yeah, so that's all my content for today's workshop. Thanks for having me here, and thanks for listening.
Awesome. Thanks a lot, Brian. Really appreciate that presentation. That's fascinating. Yeah, not a lot of questions. One of them is if we can get the GitHub repo, which you just showed. Maybe you can just send that to me, and then we can just drop that into the Akala channel afterwards.
Yeah, I will share the link of the slides to the Akala channel in the Discord server, which, well, the slides will contain all the links.
Perfect. And I dropped that Discord link for you that were asking in the channel as well. But yeah, a lot of thank yous and wonderful demo. So that was great. Really appreciate you taking the time, Brian. And yeah, if you guys have questions, join the Discord. And yeah, reach out if you guys have questions specifically about your projects. Otherwise, keep up the good work. And again, thanks, Brian. And also I want to thank Dan for helping organize and get Akala into the sponsor and being a part of the hackathon. So really appreciate the work that he's doing and everyone in the Polkadot ecosystem.
Yeah, thanks. Yeah, looking forward for some great submissions.
Cool. Have a good rest of your day. And